Swayam Prabha. Digital India. Educated India.
Hello, today we will start with the lecture 1, intermolecular forces. So, intermolecular forces, the forces between the two molecules. I have pasted two examples. One is the nucleus, which is having neutron, proton and electron, and they are very well organized through the intermolecular forces. Another example is a biomacromolecules. This is a DNA. So, you can see different molecules are organized through various hydrogen bonds and other intermolecular forces. If you remember, the DNA is organized as a helical structure. So, this is stabilized by the various intermolecular forces. Also, if you just see the proteins, they have primary structure, secondary structure, tertiary structure and quaternary structure, and all the structures are stabilized by different intermolecular forces. So, in this lecture we will just see what is the origin of this intermolecular forces, what is its historical perspective of this intermolecular forces, and also we will see few examples how intermolecular forces are calculated, what are their functions. So, let us start with the first. In the nature, uh, various forces we used to experience, and if you understand this code, so intermolecular forces embrace all forms of matter. So, in any form of matter always the intermolecular forces are involved. So, we can classify four forces. Two are the strong and weak interactions. Second is the electromagnetic and gravitational interaction. The first is strong and weak interactions. So, this acts between the neutron, proton, electron and other elementary particles, and these interactions have a very short range of action, less than 10 to the power minus 5 nanometer, and belong to the domain of nuclear and high energy physics. Other two forces are electromagnetic and gravitational interactions. So, they act between atoms, molecules and also sometime between elementary particles, and these forces are effective over a much larger range of distance. It may vary from a subatomic distance to a infinite distance. So, these are the four different type of forces which embrace all forms of matter, and these intermolecular forces ultimately determine the property of a solid, a liquid, a gas, behavior of particles in a solution, different types of chemical reactions, and as I told, organization of biological structures like DNA, RNA and proteins, carbohydrates. So, ultimately if we see, the intermolecular forces are very much responsible in all the aspects. So, these are few illustration of intermolecular forces. The first one is, you can see a nuclei where protons and neutrons are there in the nucleus. So, here these protons and neutrons, they combine the strong nuclear interactions. Also they are surrounded by the electrons, but electrons can leave the orbit, they can go to other orbit, as they are interacted through a weaker interactions or weak interactions. So, this is a very classical example of the strong and weak interaction, the nucleus itself. The interaction between proton and neutron is the strong one, and interaction with electron is the weaker interaction. Another example is the gas and liquid. So, in case of gas, they are having sort of repulsive energy. So, they live in the gaseous phase, but when they try to attract each other, the cohesive forces strong start working there. So, the gas condenses to the liquid. So, in the liquid they are attracted together, but in the gas at the same time they are experiencing the repulsive forces. Another example, this is the earth. We can see a various pictorial representation. We start with the Galileo. So, what Galileo tried, he threw two different balls. When he was throwing two balls, he understood that there is a gravitational force. Also, Archimedes, he saw if you put something in another food, you will experience the buoyancy forces. Classical example of Newton, if something falls from the top, so this was the example, apple is falling from the tree, apple is falling from the tree, this is the example of again gravitational forces. So, gravitational and intermolecular forces, it acts together to determine the maximum possible size of building, mountains, trees and animals, or you can see a system. So, these two forces, gravitational as well the intermolecular forces, they decide about the tides, they decide what should be the height of a particular building, they decide what should be the maximum size of a particular animal, how the satellites work. So, basically if you understand these forces, so they act in all form of matter, whatever we see in the nature. So, this is the historical perspective. So, earlier before 1500 or 1600, of course, there were all intermolecular forces, they are also being experienced also, sometimes for the calculation, sometimes for the Ayurveda medicines, but only like now as they were not generalized, they were not well documented, their function were not defined. So, if you just see the typical example of Newton, so it does not mean that before Newton no one experienced the apple is falling from the tree, but that phenomena, that observation was not generalized. So, it 17th century is the first, considered as the first scientific method, where we started with the Galileo, then Boyle's law, then Newton's, they derived few breakthrough theory. Boyle's law, he derived the gas law, PV is equal to RT constant. So, here gas law, it says interaction between gas molecules are repulsive in nature, but when Newton discovered the law of gravity, so he always say there is always an attractive interaction between two different molecules. The next comes yours in 18th century, because of this contradiction between repulsive and attractive force, there have been lot of confusion and contradiction in the 18th century, but of course we got few mathematical theories from the Laplace, Euler and Coulomb. So, this century is basically known as some mathematical methods as well as this Newton's Principia. Followed by this 18th century, in the 19th century we had very good breakthrough starting from Young's, then Classes, Maxwell, Van der Waal, Gibbs, Boltzmann. So, they derived basically the kinetic theory as well as the thermodynamics to understand how these intermolecular forces affect the behavior of a system. This is one example of Van der Waal equation. So, if you just see the gas law and the Van der Waal equation. So, gas law is applicable only for the gases, but in the Van der Waal they have added extra term. This is for the attractive term, this is for the repulsive term in the same equation. Now, this equation is called the equation of state. It means it can apply to the both gas as well as liquids. Then followed by in the 20th century we had Leonard Jones potentials and other law. So, here uh, the potential is defined as a function of mass between two as well as the distance between two, and later on if you see in the next slide. So, we will have both the terms in the same potential, it will have both attractive as well as the repulsive terms. So, I will just give one example of attractive forces. So, attractive forces is simple gravitational forces, one object is m, other object having mass m2, they are positioned at a distance r. The simple force between them will be m1 into m2 upon r square into g. So, g is the gravitational constant. So, this is simple attractive force. And now, as I told, Boyle's law, it says the gas is repulsive. If the gas is repulsive, then how there will be formation of solid and liquid? It means from repulsive again it is going to the attractive force between gas molecules. So, they form liquids, again attraction, they go to the solid. But after formation of solids, it does not vanish. It means again it is not attractive forces does not keep continuing. It means that is why the universe or the system exists. So, it is like repulsive, attractive and again repulsive. It is a balance between these two forces. One classical example of this attraction and attractive and repulsive forces is capillary. If we just see capillary, so there are two kind of interaction. One is interaction between liquid-liquid interaction between the liquid-liquid molecule, and second is interaction between the liquid solid interaction. So, this is called cohesion, this is adhesion. So, if you just see put the capillary tube of any wall thickness, you are going to have the same height, capillary rise. So, the interaction between liquid it prevent the capillary rise, but at the same time interaction between liquid and solid promote the capillary rise. So, this is classical example where we are seeing both adhesive as well as the cohesive forces. And in the 20th century, various intermolecular interactions and bonds were considered, their function or expressions were defined starting from this ionic interactions, ionic bond, metallic bond, van der Waals forces, hydrophobic interaction, hydrogen bonds and the salvation forces. So, this is a overview of historical perspective of the intermolecular forces. So, the 17th century is known as scientific method or first scientific method. 18th century is known as Newton's Principia. 19th century is known as mathematical methods. 20th century is known as this kinetic theory and thermodynamics, and 21st century we are continuing the continuum theory and colloidal theory. So, we will just see one example. Let us say this is your gas law, P b is equal to constant. So if we write P inversely proportional to 1 upon V to the power m, we are giving a random number m here. 1 upon V, you can write this is a density, and expression for the repulsive forces between two molecules is given by C is a constant, C is a constant, and R is distance between the, R is the distance, or you can say intermolecular distance. So this is a typical expression for the repulsive forces. Now let us see one example. We are having a cubical space, its dimension is L, and it is filled with few gas molecules whose radius is r. The total volume of the cube or system will be L to the power 3, and volume of each molecule will be proportional to the r. So if you want to calculate how many number of molecules are present, we can simply divide the volume of these two. So these L cube upon R cube number of molecules are present in the system. Now if you are talking about the pressure, pressure is always applied on the area or one side or one face of the system. So how many number of molecules are present at each side of, so area of each side will be the L square. So number of molecules will be L square upon R square. So repulsive forces between two molecules is defined as C into R to the power n. If you are having this number of molecules, the total force will be this multiplied by this. So it will be C upon R to the power n into L square upon R square. Now if I want to calculate the pressure, I have to divide this force divided by the area, and this area is L square. I am considering one side of this cube. So it is coming like C upon R to the power n plus 2. Now let us go to the experimental. What gas law suggests? Gas law suggests P equal to 1 upon V, and V can be written in terms of R cube. So this will be 1 upon R to the power cube. So if I compare this R to the power n plus 2 and R to the power 3, so it says n plus 2 is equal to 3, that means n equal to 1. So for this repulsive nature, n is coming to the 1. Further, if you want, one can generalize this n equal to 3 m plus 2. So here for the gas law, value of m is equal to 1. So if you put 1 here, so n will be coming again 1. So this proves that there is a repulsive interaction between the gas molecule. We are having this repulsive interaction between the gas molecule. So next we will start, followed by this we started with model interaction potential in the 19th century, which says the potential is simple function of mass between two and inversely proportional to the intermolecular distance between two. This is very much known as the gravitational force G, gravitational potential G m1 m2 upon R, where G is the gravitational constant, its value is written here. So from this, the model interaction potential was defined as, you have taken G as a constant C, G was replaced by C, then m1 m2, and we put the R to the power of n is another constant. So this is the potential, and typically if you want to calculate the force, you have force is the derivative of the potential. So, Fr is simply a derivative of potential. So, if you derive this, you will get n C m1 m2 r to the power n plus 1. Now, depending on the value of n in this equation, if I put n is equal to 1, if I put here n is equal to 1, then Fr will be minus C m1 m2 upon r square. If you go to the last slide, this is same gravitational force. So, what it suggested, depending on the value of n, we can decide which type of intermolecular interaction is this. Like for n is equal to 1, it is a gravitational force. So, typically gravitational force is always attractive. Gravitational force is always attractive in nature. So, typically if you go for, and also attractive, plus it is also a long range force. So, gravitational force is attractive as well as long range force. So, if you go for n is equal to 1, so it goes for the long range forces. So, typically the value of n lies in the range of 4 to 5 for the short range intermolecular forces. So, that we will discuss in the next slide. Now, one can calculate the total interaction energy. Let us say in the system, one molecule is going to interact with the all other molecules in the system. So, total interaction we have to integrate. This is the size of one molecule, diameter of the molecule, and L is the size of system. So, total number of particles will be, let us say this is, we are talking interaction at R, this is R and this is the dr. So, at this distance we are considering the interactions, so it will be 4 pi r square into dr. How many molecules? If you multiply with the number density, so these number of molecules are interacting. This is the potential between two molecule Wr, and we have to integrate from this size sigma to the L. Now, Wr potential value, if you just remember the last slide, you can write Wr as minus C upon r to the power n. So, here if you write C upon r to the power n, so it will turn out to be 4 pi C rho r to the power 2 minus n into dr. So, if you integrate this very simply, so you are going to get minus 4 pi C rho n minus 3 sigma to the power n minus 3 1 minus sigma upon L n minus 3. So, again if we just see, the total interaction energy is again depends on the value of n. So, if value is n of n is greater than 3, so we can ignore this term. So, it will be simply like 4 pi C rho n minus 3 sigma to the power n minus 3, and this is very much understood that always size of particle will be much lesser than the size of system, or you can say here sigma upon L is always less than 1. So, here again depending on the value of n, one will be able to understand whether it is a short range interaction or the long range. Typically, if it is 1, it is a long range. If it is 3, it is at the boundary between short and long range, and if it is greater than 3, 4 and 5, it goes for the short range intermolecular forces. N is equal to 1, n is equal to 3, n is equal to greater than 3, let us say 4, 5 and so on. So, this is called long range, this is at the boundary and this is the short range. So, typically depending on the n, value of n, we will be able to define whether it is a long range or it is the at the transition between short and long range or it is the short range intermolecular forces. So, this is very good example. If you just see gas law says it is having the repulsive interaction between the gas molecules. Now, if you can modify the gas law through the intermolecular interactions, so it can be applicable for the both gases as well as the liquids, because in the gas it says it is a repulsive interaction, but at the same time in the liquid it says it is coming through the attractive interaction. So, considering this, van der Waals considered the attractive effect between the molecules and he just modified. So, he added two terms P, he added a term, a attractive term, at the same time in the B volume he subtracted the terms B. So, this is a modified gas law proposed by the van der Waals, also known as the van der Waals interaction or van der Waals equation of state. So, equation of state means it can be applied to the both gas and liquids. So, as I told, this A plus V square accounts for the attractive intermolecular forces. Now, if you remember, we calculated the potential in the last slide. So, it says total energy is the 4 pi C rho divided by n minus 3 sigma to the power n minus 3. 4 pi C rho divided by n minus 3 sigma to the power n minus 3. So, this is the potential energy between the two molecules. If you want to consider for one molecules, you have to divide by 2. So, if you divide by 2, it will be same as the value of A which is coming here as the attractive force. So, if you just see the value of A is very much coming from the total interaction energy between the molecules. So, A is equal to, so this will be now it will be the 2 pi and of course n minus 3 sigma to the power n minus 3. So, it can be further broken. So, you can write C divided by sigma to the power n into 2 pi sigma to the power 3, it will go upside divided by n minus 3. So, it says again it is coming to the same expression of the potential derived here, which says potential is a function of C upon r to the power n. So, this is the potential, or you can say this is W0 and this is the molecular volume. So, the A is coming simply from the intermolecular interactions, which you can say is a proportional to the intermolecular potential into molecular volume divided by n minus 3, and simply V is the simple volume function. So, for half of the, or you can say this is V by 2. So, V will be 4 upon 3 pi sigma cube divided by 2. So, again this will be the 2 by 3 pi sigma cube. So, this is how these two terms is coming in the van der Waals equation, and again this is very interesting example. Gas law is only considers the repulsive intermolecular forces, but the equation of state consider both attractive as well as the repulsive intermolecular forces. So, term A comes for the attractive correction for the attractive forces, and B is the correction for the repulsive interactions. So, as we see in most of the cases we are going to have both attractive as well as the repulsive intermolecular forces. So, Mai in 1903 he proposed very interesting pair potential which accounts for both attractive as well as the repulsive term. So, one term is attractive, other term is repulsive in this, and this is also known as the Mai potential, and here the constant A and B can be related to the A and B of the van der Waals forces or van der Waals equations. Later on, this Leonard Jones modified the value of N and M. He proposed the value of 6, N is equal to 6 and M is equal to 12. So, this is for the attractive term and this accounts for the repulsive term. So, this is very good to see that especially this depending on the value of N or you can say the M, this pair potential can be applied for the different systems. So, we will see in subsequent slides. Okay, so we will just discuss one example here. So, this is a typical Leonard Jones potential, which says this is the attractive term, this is the repulsive term, and typical value of A and B, let us consider 10 to the power minus 77 and 10 to the power minus 134. So, we will just see how this force or potential vary with the distance. So, with the above value of A and B, can we calculate what is the minimum value of potential and what will be the maximum adhesion force in the two atoms, and whether whatever the force is coming between the two atoms, can it be measured experimentally. So, this is force and energy as a function of intermolecular separation or the intermolecular distance. So, if the distance is high, so before that I will just say the positive is the repulsive, negative is the attractive. So, these are the attractive range, these are the repulsive range. Okay. So, if the distance is very high means it is a larger distance. So, for the larger distance between two molecules are interatomic, so we are going to have the attractive forces. So, attractive forces is keep on increasing up to the here, or you can say attractive potential is increasing up to the here, and suddenly if you come very closer, it suddenly goes to the repulsive side. So, here is the transition, it goes to the minimum. So, minimum means this is the equilibrium. Equilibrium between the two particles where we are going to have the minimum energy or the minimum potential. This is the equilibrium point. If you come even closer to the equilibrium, again it will go to the very much to the repulsive side. So, once this function is known for the potential, the similar function we can calculate for the force, simply F minus dW upon dr. So, the first part was what should be the W minimum. So, for W minimum, you know, if you want to calculate the minima of a function, then WR minus A upon R to the power 6 plus P upon R to the power 12. If you want to calculate minimum, you have to say dW upon dr equal to 0. So, dW upon dr will be 6 A upon R to the power 7 minus 12 B upon R to the power 13. And if you put this value as 0, so we can simply get the value of R. So, R will be, if you compare this, 12B upon 6A, 12B upon 6A to the power 1 upon 6. So, you can say 2B upon A to the power whole 6, and so its value is coming out to 0.355 nanometer. This is also called the RE, equilibrium. As I told, where the minimum force comes, that is known as the equilibrium point. So, it is coming 0.355 nanometer. Now, once RE is known, we can calculate WRE. So, here WRE in the same function, in place of R we have to write the RE, and we can calculate the value of W minimum, and it is coming out to be minus 2.51 into 10 to the power minus 21 joule, but it is asked to calculate in terms of kT. So, kT is the thermal energy. kT is, we say kT as kT as thermal energy. And value of K is 1.381 into 10 to the power minus 23 joule per Kelvin, and temperature in the problem was given as 298 K. T was given as 298 K. So, this energy can be calculated in terms of thermal energy. So, it is coming out to be 0.61 kT. So, this is the first part. Now, if you remember the problem, the second part says what should be the maximum adhesion force between the two atoms. So, again you have to follow the same exercise as we did for the minima. So, let us start with the value of F. So, F is defined as minus dW upon dr. So, Fr will be 6 A upon R to the power 7 minus plus 12 B upon R to the power 13. So, again you have to calculate here dFr upon dr, or you can simply say you have to calculate d2W upon dr square, that is equal to 0. And if we solve this, so this R value will say the value where we will have the maximum force. So, if I integrate it further, so and put it 0, so we will get R is equal to 26 B upon 7 A to the power 1 by 6, 26 B upon 7 A to the power 1 by 6, and this R is known as the RS. RS means separation, the force, the distance where the separation between two molecules will take place, and it is coming out to be 0.39 0.3935 nanometer, 0.3935 nanometer. If you take the ratio of Re and Rs, Re means the value where there was the equilibrium, means potential was 0, Rs is the distance where the maximum force is there, the ratio is coming to the 1.24. This is a typical value we always consider Re upon Rs as 1.24. So, of F max you can calculate the value of F. What you have to do here, in place of R you have to write the value of Rs. So, its value is coming out to be 1.89 into 10 to the power minus 11 Newton, or you can say 18.9 piconewton. Now, this value is coming 0.3935. 3935. Just see, very interesting. At nanometer level, at 0.35, it was having the minimum value of energy, but at the same time we are observing separation at a potential maximum force at 0.3935. Just see, this is if you just see 0.35, 0.39, it's not much different. Also, we'll just see the value, the distance at which we are going to have the zero potential. So, if you want to just say the zero potential, means the value of WR should be 0. If you simply put the value of WR should be 0, so the R naught will be here B upon A to the power 1 by 6. It is very simple. R naught will be B upon A to the power 1 by 6. And if you calculate this R naught, so it is coming to be 1 point R naught, this R naught one need to calculate, and the ratio of Re upon R naught is coming to the 1.12. So, we have got two ratio, Re upon R naught 1.12 and Rs upon Re is equal to 1.24. If you just see, this is just a factor of 1, even not a factor of 2. So, here very interesting observation. So, if you just see the Lennartzian potential at this distance, potential is 0, at the same time at the factor of 1.12, its value is the minima. At the same time at the factor of 1.24 between these two, the maximum force is observed. So, if you now we can try to understand that even the separation distance at the some nanometer level, we are playing between 0.3 to 0.4, and we are observing three different phenomena: zero potential, a minimum potential, also at the same time the separation distance. It is very interesting. That is why this intermolecular forces, especially that at the interatomic separation, even at the angstrom or nanometer level, play a very important role towards the understanding the system. So, now if you remember here, so these intermolecular interactions, it decides whether your molecules will remain in gas phase, or they will be in the liquid phase, or they will be in the solid phase. So, now let us summarize here. So, we started with this 17th century known as the first scientific methods, where this Boyle's, Galileo and Newton's established some generalized understanding or generalized force function, and then this 17th century is known as this lot of confusion and contradiction, because difference between the attractive and repulsive nature of the forces. But of course, we had few mathematical expressions, Euler, Laplace in this century, Then followed by the 18th, 19th century, we had kinetic theory of gases, thermodynamic principle. So here we try to relate how these intermolecular interactions affect and define the physical and chemical properties of a system. So that we studied in the 19th and 20th century. Then again in 20th century we started with the quantum theory and colloidal interactions. So these are the different intermolecular forces which have emerged with time: ionic bonds, metallic bonds, van der Waals forces, hydrophobic interactions, hydrogen bonding, and solvation forces. So about these forces we will be discussing in the next lecture, uh, how they are expressed and what is the function of these forces. So in the recent followed by after the 20th century, to understand the very simple systems, so I have listed few examples: liquid structures, surface and thin film phenomena, complex fluid, soft matter, self assembly, quantum dots, and biointerfaces, means how the biological molecules come and interact with the surfaces. So recently also we developed some mathematical methods like Monte Carlo molecular simulations, which analyze the things at molecular level. Also we have developed some molecular docking, determination of binding site. So these phenomena again focus specifically to the short range intermolecular forces. But if you go for colloidal system, colloids, it talks about again the long range intermolecular forces. So colloids, how two different protein molecules are suspended or any nanoparticle are suspended in the system. These are the few examples of the colloidal systems. So again, apart from those forces, we come up with some electrical double layer, Stern layer. So these are the some recent trends in intermolecular forces or intermolecular interactions which is evolving with the time. And very interesting is if first we understand the how intermolecular forces affect the physical and chemical property of the system. Now we are understanding how this intermolecular forces defines the behavior, the property of the simple systems like liquid structures, surface and thin film formation, complex fluid, biointerfaces, self assembly of molecules. So we will conclude this lecture here, and in the next class we will start the classification of various intermolecular forces, their different functions, how these intermolecular forces define the behaviors or properties of systems. Thank you.